Welcome to AI Paper Slop. Today's paper is OmniReasoner, Thinking with Long Audio-Video via Native Tool Use.
Right, by Yu Chen, and a joint team from the University of Chinese Academy of Sciences, Institute of Automation, CAS, Shopee, and Tsinghua University.
Yeah, and we are getting straight to the core insight today because this paper tackles, honestly, the absolute computational nightmare of long audio-video reasoning.
It really is a nightmare.
Right, because processing an hour-long video uniformly at high fidelity, it just blows up your context windows and your compute budgets. But if you just downsample the video to save memory, you end up destroying all the sparse evidence.
Exactly, like a split-second visual cue or really brief background sound is just gone.
Totally gone. So OmniReasoner solves this by teaching Omnimodal LLMs to use this native zoom-in tool via post-training. Basically, the model skims a cheap, low-resolution global preview, decides exactly if and where it needs more info, and then calls a tool to fetch a dense, high-fidelity local clip.
And to make that dynamic zoom mechanism actually function, they had to solve a massive temporal alignment problem. So the authors introduced TimeAnchor.
Which is super cool.
It is. It's a brilliant but really simple, text-based, absolute timestamping method. It keeps temporal arguments valid across totally different sampling resolutions.
Right.
And they trained this pipeline using a fully automated Temporal Augmented Data Engine for the supervised fine-tuning, and then followed that up with Group Relative Policy Optimization, or GRPO.
Okay, so let's unpack this uniformity dilemma first.
Yeah.
Because anyone working with these models hits this fundamental bottleneck almost immediately. You feed a 2-hour video into an omnimodal model, and the math just doesn't work out.
No, it really doesn't.
If you try to process 30 frames per second plus all the audio tokens, your context window overflows before you even finish, like, the first act of the video.
Yeah, the compute cost is just astronomical. So the standard engineering workaround is to aggressively drop frames, right? You might sample, I don't know, 1 frame every 2 seconds.
Just to create a sequence that actually fits.
Exactly. But the trade-off there is severe. You're effectively rolling the dice on whether you keep or delete the specific piece of evidence you actually need to answer a prompt.
Because that critical evidence might be super localized, like someone dropping a key on a desk or a really subtle change in facial expression.
Or a crucial piece of dialogue that literally lasts half a second. If that happens between your sampled frames, the model is just flying blind.
Which kind of brings up the current landscape of agentic systems. Because we do have models that attempt to manage their own attention, but they heavily bias toward spatial visual evidence.
Right. They figure out where to look on an XY grid within a single frame.
Yeah, like finding a tiny object in a high-res image. They don't naturally treat video and audio as this coupled continuous timeline where the model has to actively manage its temporal budget.
And that's exactly the gap OmniReasoner fills. It teaches the model to jointly decide what to look at, what to listen to, and crucially, when the interaction between those two modalities is the deciding factor.
It's a huge shift from static processing to this interactive workflow. I mean, it's like trying to find a specific clue in a 2-hour movie. As humans, you don't watch the whole thing frame by frame from start to finish.
No, of course not. You scrub the progress bar.
Exactly. You scrub the bar, you glance at the sparse thumbnails, and only when you spot something relevant do you stop, hit play, and actually listen to the audio at normal speed.
And OmniReasoner operationalizes that exact behavior. So it takes the long audio-video input and constructs what they call a global observation.
Which is the equivalent of those scrubbing thumbnails.
Right. It has a super low perceptual cost because it's a sparse sampling of the frames. It preserves the broad temporal structure of the video.
So you can tell when a scene changes from, say, a kitchen to a highway.
Exactly. But without eating up your whole token budget. And from that sparse global view, the model's policy basically faces a binary choice. It can output an answer action, meaning, the user's prompt was simple enough that the broad context is totally fine.
Okay, or what's the other option?
Or it can output a zoom action passing in an interval in seconds. Like zoom 32 to 38.
Oh, wow.
Yeah, and when that zoom action is invoked, the environment actually halts the model's generation, goes back to the original dense source files, and cuts a high-fidelity local clip of both the video and audio for that exact 6-second time frame.
And then feeds it back in.
Yep, feeds it back into the context window. So the model then generates its final answer conditioned on both the initial sparse context and the new zoomed evidence. What's fascinating here is that this temporal zoom-in isn't a fixed preprocessing rule. It's a learned tool use behavior.
Here's where it gets really interesting, though, because Wait, I have to push back on the mechanics of that zoom call.
Okay, go for it.
If the first pass is, say, 1 frame per second, and the zoomed pass is 30 frames per second, the raw token positions are completely decoupled from absolute time. A standard transformer architecture doesn't inherently understand seconds.
Right. It only understands token sequence positions.
Yeah, so if I tell a model to look at frame 100 from a sparse video, that's a completely different moment in time than frame 100 in a dense video. So how does the model even know what timestamp to ask for? Doesn't changing the sampling density completely break the frame index?
You hit the nail on the head. That granularity mismatch is usually exactly what breaks tool argument grounding in these multimodal systems.
Okay, so how do they fix it?
Well, QuenOmni, which is the base model they used, processes streams by splitting them into 2-second chunks by actual time. And for each chunk, it puts the visual tokens first, then immediately follows with the audio tokens.
Right.
But the internal clock is implicit. It relies entirely on the frame index relative to the sampling rate. So the moment you change the sampling grid to pull that dense clip, chunk number 10 no longer corresponds to the same temporal moment.
Plus, the audio tokens don't follow the visual frame number, which just makes it worse. So if you rely on the implicit token index, the model basically hallucinates timestamps the moment the resolution shifts.
Exactly. It would request a zoom on an interval, the density would change, and the model would completely lose its place. So to solve this, the authors introduce TimeAnchor.
Okay, tell me about TimeAnchor.
The inspiration comes from media systems like FFmpeg, which align discrete audio and visual streams by mapping everything to absolute wall clock time. Instead of relying on sequence position, TimeAnchor prepends a plain text marker to the front of every single 2-second chunk.
Wait, like literally just text?
Literally just text strings like bracket 0s, bracket 2s, bracket, right before the media tokens.
So it's like putting absolute mile markers on a highway instead of telling a driver to, drive for 5,000 tire rotations.
That's a great way to look at it.
Because the tire size, which is your sampling density in this case, might change depending on the car you drive. A dense video takes a lot of rotations, a sparse video takes a few, but mile marker 32 is always mile marker 32.
Exactly. And that elegance is really the best part of the paper. Because normally, whenever you try to solve localization, the instinct for engineers is to add special tokens to the tokenizer.
Which is a huge pain.
It is. You have to modify the embedding layers, run expensive pre-training to teach the model what those new tokens mean. It's awful. But by using plain text strings that the base LLM already understands, there are absolutely no architectural changes required.
No separate localization objective in the loss function either, I assume?
Nope, none. It simply binds the interleaved video and audio tokens to absolute wall clock time. So when the model says zoom 32 to 38, it universally means seconds 32 to 38 across the whole system.
That's incredibly smart.
Yeah.
Okay, the architecture makes sense, but teaching a cold start model to reliably use this tool feels like a massive data acquisition problem.
Oh, yeah.
Getting human annotators to sit down with hour-long videos and manually label the exact start and end seconds of the evidence needed for a specific question that would cost an absolute fortune.
It's prohibitively expensive and super slow, so they bypassed human annotation entirely. They built a temporal augmented data engine that synthesizes post-training trajectories using automated video editing.
Oh, nice.
Yeah, they set up this FFmpeg-based pipeline they call Media Sandbox. It essentially constructs long-form reasoning tasks where the exact evidence intervals are known purely by the mechanics of how the video was assembled in the first place.
So they construct the needle in the haystack themselves, meaning they automatically know where the needle is.
Exactly.
How does the Media Sandbox actually stitch these together, though?
They rely on two main data generation methods. The first is multi-segment composition. They take a bunch of independent short clips that already have established question and answer pairs.
Okay.
And the automated engine stitches several of these totally unrelated clips together into one continuous massive video. It then assigns the question from just one of those source segments as the prompt for the whole thing.
Ah, I see. And because the Python script executed the concatenation, it just logged the exact start and end offsets of that target clip.
Right. Those temporal offsets instantly become the ground truth interval label for the zoom tool.
That's so clever. It basically turns a standard visual QA task into a temporal search task. So what's the second generation method?
Anomaly insertion. The engine takes a continuous long audio-video stream and replaces a really specific temporal window with a completely different short clip.
Like it just overwrites a section.
Yeah, it might overwrite just the audio stream, just the visual stream, or both at the same time, and the model's assigned task is to identify the anomaly and localize it.
And once again, because the sandbox did the overwrite, the exact window of replacement is automatically your interval label.
Precisely.
Okay, using automated tools to generate the labels is super smart. But wait, so what does this all mean for the training quality? If they use massive teacher LLMs, like Gemini, to generate these reasoning trajectories, how do they stop the teacher from just cheating and leaking the hidden timestamps directly into the reasoning trace?
This is a classic pitfall in synthetic data generation. If the teacher model doesn't experience the struggle of actually searching, the student model won't ever learn the logic of searching.
Right, because if you feed Gemini the metadata and say, hey, the anomaly is at minute 45, Gemini's just going to output, I know the answer is at minute 45, so I will zoom there.
Exactly, which teaches OmniReasoner nothing about actively searching a sparse preview. So to fix this, the researchers use a technique called hindsight synthesis. For the longer videos, the teacher LLM is given the reference answer and the interval as guidance, because it needs that to know what the target is.
But I'm guessing the system prompt explicitly tells it not to leak it.
Yes, the prompt strictly forbids the teacher from leaking that supervision into the generated text. It forces Gemini to play dumb, essentially.
So it instructs the model, like you know the exact timestamp, but you have to pretend you're a first-time viewer.
Right. It demands a causal justification based purely on the sparse evidence. Tell me what subtle, observable cues in the low-res global preview at minute 45 would motivate someone to zoom in for a closer look.
That's fascinating. So the resulting text actually looks like genuine first-pass reasoning.
It does. But they don't just trust the prompt to work perfectly either. The engine runs the outputs through automated LLM judges to aggressively filter the generated data.
Oh, to catch any slip-ups.
Yeah, if the judge detects that the teacher accidentally used quotes directly from the hidden supervision, or if the reasoning trace shows obvious clairvoyance without pointing to a real visual or auditory cue, that trajectory gets thrown out immediately.
Ensuring the resulting dataset for supervised fine-tuning genuinely models the investigative process. That is wild.
And that SFT phase is crucial. It trains the model on this clean dataset so it learns the basic vocabulary and grammar of the task.
It figures out how to format a direct answer when the preview is enough, and how to format a zoom request with valid intervals when it needs more detail.
Exactly. But SFT is essentially behavioral cloning. It teaches the model how to use the tool, but not necessarily the optimal strategy for when to use it to maximize accuracy.
Right, because behavioral cloning often falls short in really complex decision-making environments.
So this is where the agentic reinforcement learning comes in, right?
Yes. They transition from SFT to RL, specifically using Group Relative Policy Optimization, or GRPO. Now, if you're working in reinforcement learning, you're probably used to Proximal Policy Optimization, PPO.
Which requires running a totally separate value model alongside your policy model to estimate the baseline advantage.
Right. And that value model consumes a massive amount of memory,
Right.
which is a huge issue when you're already dealing with really heavy multimodal inputs like hour-long videos.
So GRPO bypasses the need for that separate value model entirely.
It does, which frees up vital compute for the actual video processing. That's a core mathematical advantage here. Instead of predicting a baseline value, GRPO samples a group of different trajectories directly from the policy model for a given prompt. So, like, the model might try 4 different approaches.
Exactly. One trajectory might try to answer immediately, one zooms into the first 10 seconds, one zooms into the middle, and one zooms into the exact correct timestamp. The system calculates the final rewards for each of those trajectories and then normalizes them against the average reward of that specific group.
Ah, so it computes a relative advantage.
Yes. The trajectory that zoomed to the correct timestamp gets a positive advantage score, the others get negative scores, and the policy updates its weights to favor that successful behavior.
That's incredibly elegant. And the reward function itself is actually super streamlined too, right? Because the equation is simply R equals R accuracy plus R format.
Right. They check if the final answer is factually accurate, and they check if the model used the proper XML tags and valid temporal intervals.
But notice what's missing there. There is absolutely no separate reward for localization. They don't give the model partial credit for zooming into the right timestamp.
Exactly. The predicted interval is optimized purely through its causal effect on getting the final answer correct. If zooming into a specific timestamp reveals the high-fidelity evidence you need, you get the answer right and you get a high reward.
And if it hallucinates a timestamp, zooms into random noise, and gets the answer wrong, it just gets penalized.
By tying the reward strictly to task completion, the model learns to localize evidence completely naturally. It stops the policy from learning degenerate behaviors where it just arbitrarily uses the zoom tool over and over just to farm localization points.
Which happens a lot in RL. But this actually raises an important question. If the RL stage is so powerful at discovering the utility of the tool based just on final accuracy, why bother with the complex data engine and the SFT stage at all?
That's a great question.
Couldn't we just use GRPO on a base model and let it figure out the zoom mechanics from scratch through trial and error?
You'd think so, but the authors ran comprehensive ablation studies to test that exact hypothesis. And when they skipped the SFT stage and attempted to train the base model directly with RL, the performance completely collapsed across all benchmarks.
Wait, really? Collapsed entirely?
Yep. A cold start omnimodal model is incredibly reluctant to explore complex tool use in such a high-dimensional space. I mean, the search space of an hour-long video is simply too vast for random exploration to reliably hit the correct timestamp.
So it never gets a positive reward signal.
Exactly. The model just gets stuck in a loop of guessing the answer directly from the sparse global view, failing, and never learning that the zoom tool is actually the solution.
That makes total sense.
Even when the researchers attempted to force exploration by using a structured template that mandated tool use, the direct RL policy drifted so severely during training that it suffered format collapse.
Oh, so it just completely forgot the basic syntax of how to write valid intervals.
Rendering the tool completely useless. So the SFT stage is a totally non-negotiable prerequisite. It instills the structural vocabulary and the basic logic of searching. And then the RL stage acts as a refinement layer, optimizing the execution against the environment.
Okay, so the combination of SFT and GRPO yields some pretty massive benchmark results. Based on Qian 2.5 Omni 7b, OmniReasoner jumps from a baseline score of 29.3 to 34.8 on the Omni Video Bench evaluation.
And on video homes, the leap is even more pronounced. It goes from 24.4 to 40.0.
That is a huge jump.
It really is. And when you break those results down by video length, you see exactly why the zoom tool is so impactful. The performance gains correlate directly with the temporal length and therefore the difficulty of the search task.
So for longer videos, the gains are even bigger.
Much bigger. For videos that span 10 to 30 minutes, OmniReasoner achieves a 9.9-point gain over the baseline model. Furthermore, the tool call rate scales organically with the input length. So for short videos under a minute, where the global preview is already relatively dense, the model only decides to call the zoom tool about 33.3% of the time.
Because it doesn't need it.
Exactly. But on the Omnibench dataset, dealing with videos that are 50 to 90 minutes long, the model actively chooses to use the zoom tool 93.6% of the time.
It literally learned that attempting to skim a 90-minute video in one shot is statistically useless without zooming in to verify the details.
Yes. It fundamentally understands the limits of its own perceptual resolution.
That is incredible. It proves that the model isn't just blindly following a rigid script. It's dynamically assessing the entropy of the input. It evaluates the global observation, recognizes when the uncertainty is too high, and proactively allocates compute to fetch higher resolution data.
It treats the video not as a static document to be parsed, but as an interactive environment to be navigated.
Honestly, for those of you building agentic AI systems, the paradigm shift here is moving away from the brute force approach. We have spent the last few years just indiscriminately expanding context windows, trying to shove millions of tokens of uniform, dense data into a single prompt.
And we're hitting the physical limits of memory bandwidth doing that, especially with video and audio.
Exactly. OmniReasoner demonstrates that it is vastly more efficient and demonstrably more accurate to give models agency over their own compute allocation through native tool use and absolute time anchoring.
It really is the path forward for these huge modalities.
And it leaves you wondering how this architecture could map to other domains defined by massive sequential data. Think about it. What if an LLM analyzing a massive enterprise code base could use a text-based TimeAnchor equivalent to globally skim thousands of repository files at low resolution?
Oh, that's an interesting thought.
Instead of requiring a 2 million token context window to hold the whole repo in memory at once, it could dynamically use a native zoom tool to pull high-fidelity execution traces, abstract syntax trees, or specific Git commits only when it spots an anomaly in the global architecture.
That would be incredibly powerful. We are really just scratching the surface of models actively managing their own attention spans.
We really are. Well, if you want to dig into this yourself, you can find the OmniReasoner codebase and explore the TimeAnchor implementation over on their GitHub repository. Keep experimenting, and we'll catch you on the next deep dive into the source material here on AI Paper Slop.